recording is the practice problems in Module 11 in physics. So we're just going to work through those 10 practice problems. Number 1 says, what is the speed of sound in air that has a temperature of 90.0 degrees C? So 90.0 degrees C is the temperature. It's almost 200 degrees Fahrenheit, so pretty hot temperature. Velocity is equal to 331.5 plus 0.606 times the temperature, which is 90.0. And then we don't put any units in any of the numbers within the calculation, and then our final units are just going to be meters per second. So this is going to be 331.5, and if we do this and we're allowed 3 significant figures, that comes out to 54.5. So now we're adding, and so that when adding and subtracting, we take the number of significant figures is based on the place value. So since here we went out to the tenths place, then our answer can go out to the tenths place. So our answer should be 386.0 meters per second. Okay, so we went out to add that 0.0 because we can go out to the tenths place. Okay, so that's number 1. Let's go ahead and move on to number 2. So number 2 says the frequency of a sound is 1,621 hertz, and the temperature is 30.0 degrees C. What is the wavelength? Okay, so we know that frequency is equal to velocity divided by wavelength. Where we have the frequency, we're asked to find wavelength, so we need to find velocity. So again, using that same formula. So 331.5 plus 0.606 times 30 0.0, and our units are going to again be meters per second. So when we do this part here, we can have 3 significant figures. So that is going to give us 18.2. And again, this is out to the tenths place, so when we add that to the 331.5, we'll take our answer out to the tenths place. So the velocity is 349.7 meters per second. Okay, so now all we need to do then is take our equation and solve for the wavelength. So frequency is equal to velocity divided by wavelength. So we'll multiply both sides times wavelength. That gets rid of that over there. Divide both sides by frequency. That gets rid of that over there. So then wavelength is equal to the velocity divided by the frequency. Okay, so we just said that the velocity was 349.7. So 349.7 meters per second. And we'll divide that by the frequency that we are given, 1,621 hertz, which is a 1 over second. So our seconds are going to cancel. We'll be left with meters for wavelength, and we can have 4 significant figures here. So our answer should be 0.215 0.57 meters for the wavelength. Okay, that is number 2. Number 3, what is the temperature of a 545 hertz sound that has a wavelength of 0.651? Okay, so this is the frequency, and the wavelength is equal to 0.651 meters. Okay, so again, we know that frequency is equal to velocity divided by wavelength. So to get to the temperature, we need to get to the velocity. So let's just multiply both sides by wavelength to give us that velocity. So wavelength times frequency will give us velocity. So 0.651 meters times 545 1 per second will equal the velocity. And if we do that, and we can have 3 significant figures, we should get the velocity is equal to 355, and we have meters over seconds. Meters per second equals the velocity. Okay, then we can now look at our equation for velocity of sound. So we know that velocity is equal to 331.5 plus 0.606 times t. Okay, so we know the velocity is 355. So 355 meters per second equals 331.5 plus 0.606 times t. Okay, so we're just going to solve now for t. So we'll subtract this from both sides and divide that. Divide both sides by that. So 355 meters per second minus 331.5 meters per second divided by 0.606 will give us t. Okay, so when we do this top part of the equation, since 355 is just out to the whole number place, then we will have 355 I think this is going to be 24. We can only go out to the whole place, divided by 606. So this is going to be 24. Yeah, so you're going to get 23.5, but you can only go out to the ones place because of this, and you're subtracting there. So 24 divided by 0.606 will give us, we can have 2 significant figures. So the temperature should be equal to, it's 39.6, but I think we're going to end up with 40 degrees. Yeah, this will come out to 39.6. But this 24 limits us to, actually, I guess, yeah, that's going to limit us to 2 significant figures. So I guess we're going to have to express this as 4.0 times 10 to get our two significant figures. Okay, so that is number 3 in those practice problems. Okay, number 4 says you decide to measure the speed of sound with the help of a friend. The friend stands 450 meters from you. And bashes 2 cymbals together. You determine that the time between when you see the cymbals crash together and when you hear them is 1.29 seconds. What is the speed of sound according to your measurement? Okay, so we assume that because light reaches you instantaneously, that you're going to see those cymbals go together as soon as the instant that they are clashed together. And when you hear the clash of the cymbal is simply going to be due to the speed of sound. Okay, so we know that distance is equal to speed times time, or velocity times time. So then distance divided by time will equal the speed of sound, or the velocity of sound. So the distance was 450.0 meters. The time was 1.29 seconds. So with 3 significant figures, you should get 349 meters per second. Okay. Okay, number 5. Number 5 tells us that the thunderclap from a lightning flash is heard 4.2 seconds after the flash is observed. So the time then is 4.2 seconds. If the temperature is 20 degrees, how far away was the lightning formed? Okay, so again, we assume that we see the lightning flash instantaneously, and then you hear the thunderclap 4.2 seconds later because the speed of sound is slower than the speed of light. Okay, so distance divided by time will give us the speed. Okay, so that's the equation we just did. And then we should then be able to determine how far, we should be able to determine the distance using that equation, but first we need to know the speed of sound. So the speed of sound, the velocity of the sound is equal to 331.5 plus 0.606 times the temperature, which is 20.0 degrees C. So here we can have 3, when we do this multiplication, we can have 3 significant figures. So this is going to be 12.1. And then we'll add it to that, and we can go out to the tenths place. So this should be 343.6 meters per second. Okay, so that's our velocity. And then we know that distance is equal to the velocity times the time. So 343.6 meters per second times 4.2 seconds So those seconds will cancel. We'll be left with just meters. So that the distance with two significant, so when you do this, you're going to get 1,443 meters, I think. But we can have only two significant figures. So we would have to say this is 1,400 meters. Okay, so the lightning was 1,400 meters away if it took 4.2 seconds for the thunder clap to be heard. Okay, number 6. A flutist or flautist is playing a middle C, which has a frequency of 278 hertz. The flautist is standing in the bed of a pickup truck, which is moving away from you with a speed of 25.6 meters per second. And we're told that this is away from you. What frequency will you hear if your temperature is 25 degrees C? 25.0 degrees C. Okay, so if the truck is moving away from you, that means that you are going to hear a lower frequency than is observed. So frequency observed is equal to the velocity of the sound plus or minus the velocity of the observer divided by the velocity of the sound plus or minus the velocity of the source. And then we'll multiply all that times the true frequency. Okay, so the velocity of the observer is going to be 0, right? So the observer is not moving, so we can put a 0 in here. And we are told that, so in order to get a observed frequency that is lower than the true frequency, then are we going to add or subtract the velocity of the source? We're going to add it, because if we add a bigger number, if we have a bigger number on the denominator, that's going to lead to a lower frequency. Okay, so we're going to add the velocity of the source to the velocity of the sound. Okay, so the first thing we have to do is, well, we can go ahead, I guess we can go ahead and put the velocity of the source in here, because we're told that that is 25.6. So we're going to add 25.6 meters per second. Okay, so then we're just left with figuring out the velocity of the sound. So the velocity of the sound is equal to 331.5 plus 0.606 times 25.0. And that'll all be in meters per second. So the velocity of the sound, when we do this with 3 significant figures, this is going to come out to 15.2. And then we're going to add that to that, and our answer will go out to the tenths place. So this should be 346.7 meters per second. And you do all of that. Okay, so now we can put that number up here, the velocity of the sound. So 346.7 meters per second plus 0, because the observer is not moving, divided by 346.7 meters per second plus 25.6 meters per second. So then if we do this math and multiply, so what you'll get here is you'll get 346.7 meters per second. Okay, when we add these, we can go out to the tenths place. So that would be 300, excuse me, 372.3 meters per second, and then multiply that times 278 hertz. And therefore, the frequency that is observed comes out to, with two significant figures here, because now we're multiplying and dividing, I'm sorry, three significant figures, because now we're multiplying, you're going to get 259 hertz. So as we said at the beginning, the frequency that you observe is going to be less than the true frequency. Here's the true frequency, because the truck is moving away from you. Okay, number 8. The wavelength of indigo light is 442 nanometers. What is its frequency and what is its energy? Okay, so we know that frequency is equal to velocity divided by wavelength. And the speed of light, which you will be given on a test, is 3.0 times 10 to the 8th meters per second. We will divide that by the wavelength, 442 times 10 to the negative 9 meters. So 10 to the negative 9 is what a nanometer is. So the meters are going to cancel. You'll be left with 1 over seconds, which is hertz. And if you do this, you should end up with 6.8 times 10 to the 14th 1 per second, or hertz. And we can have two significant figures because of the speed of light at 3.0. Okay. If you chose to, you couldn't just put this as 4.42 times 10 to the negative 7. It doesn't matter. I just keep it as 442 times 10 to the negative 9. But if you got 0.68 times 10 to the 15 hertz, that's obviously the same thing. So either answer is fine, as long as you have the number of significant figures correct. Okay, so the frequency is 6.8 times 10 to the 14 hertz. Okay, so then we're asked to find the energy. Well, we know that energy is equal to Planck's constant times frequency. So energy is equal to Planck's constant times frequency. You'll be given Planck's constant, so energy is equal to 4.14 times 10 to the negative 15 electron volts times seconds. And then we'll multiply that times the frequency, which was 6.8 times 10 to the 14 hertz, which is 1 per second. So the seconds are going to cancel. You'll be left with just electron volts. And with two significant figures, you should get 28.1 times 10 to the negative 1 electron volts, or you could write this as 2.8 times 10 to the 0, 10 to the 0 electron volts, which is just 2.8, right? So 2.8 electron volts should be your answer for number 8. Okay, number 9 reads that the work function of gold is 531, so we have gold, and its work function is 531 electron volts. So that means that if gold has this much energy, the electrons will have the ability to escape from the metal, from the gold. What is the lowest frequency of light that will result in electrons being liberated from the metal? What is the wavelength of the light? If light of wavelength lower than the wavelength was shown on the metal, would the electrons be liberated? Okay, so we know that E is equal to HF. So the first question we want to ask, what is the lowest frequency to liberate the electrons from the metal? Okay, so we are given that the energy is 5.31 electron volts. You will be given a Planck's constant, 4.14 times 10 to the negative 15, and that's electron volts times seconds. And then you multiply that times frequency. So we're gonna solve for frequency by dividing both sides by this. So divide this by that. That's going to get rid of this over here. Okay, so see the electron volts are going to cancel. You'll be left with 1 over seconds, which is hertz for frequency. So what you should get then is 1.3. And I don't think I have the right number of significant figures, so I should get another significant figure here. Let's see, 5.31 divided by 4.14. I should have 1.28. Okay, so we should be able to go at 1.28, 1 per second, or 1.28 hertz. Okay, so as long as the frequency of the light is 1.28 hertz, then the electrons would be able to escape from the metal, which in this case is gold. Okay, so this is our frequency. So then the next question that they ask is, what is the wavelength? Okay, so we know that frequency is velocity divided by wavelength. So we're just going to multiply everything. We want to figure out the wavelength, so multiply both sides by wavelength, divide both sides by frequency. So wavelength is equal to velocity divided by frequency. Okay, so our velocity is the speed of light. And we just saw that our frequency was 1.28, 1 per second. Okay, so the seconds are going to cancel. You'll be left with meters. And if we do that math, you should get actually no, let's go back. I didn't do that math correct. So let's go back to that previous part. So frequency is equal to 5.31 electron volts. I left the exponents off. divided by 4.14 times 10 to the negative 15 electron volts times seconds. So the frequency should actually be 1.28 times 10 to the 15 hertz. Okay, when we did this previously, so the lowest frequency that's required for the electrons to escape from the metal will be 1.28 times 10 to the 15. Okay, now we can go ahead and wavelength is equal to velocity divided by frequency. So the velocity is going to be the speed of sound. And we'll divide by the frequency, which we just determined to be 1.28 times 10 to the 15 hertz, which is 1 per second. Okay, so seconds are going to cancel, but you'll be left with meters. So the wavelength will be equal with two significant figures, 2.3 times 10 to the negative 7 meters. Okay, so that's the wavelength. And then the last question in this one says, if light of a wavelength lower than that wavelength were shown on the metal, would the electrons be liberated? Okay, so if this is the wavelength, if you decrease the wavelength, what is going to happen to frequency? Frequency is going to increase. So we already showed that as long as your frequency is this, you will liberate the electrons. And remember, it is frequency that determines whether they get liberated. So if we decrease the wavelength, that's going to increase the frequency so that the frequency is even higher than this. So yes, if they can be liberated at this, they will certainly be liberated at a higher frequency. Okay, that's number 9. The last one, number 10, states light of a wavelength of 211 nanometers. So wavelength is equal to 211 nanometers. And it's shown on copper. And the work function of copper is 4.94 electron volts. What is the maximum kinetic energy of the electrons that are emitted from the metal? Okay, so remember, the work energy is how much energy is required to liberate the electrons. So it will use, if it just has this much energy, it will use all of that energy to do so. So it would have no have no kinetic energy left. But if it has more than this amount of energy, then the rest would go into kinetic energy. Okay, so we are given wavelength. The first thing we have to do is we know that energy is equal to h times f. So we've got to get this wavelength into frequency. So frequency is equal to velocity divided by wavelength. So it's going to be 3.0 times 10 to the 8 meters per second. And we'll divide that by 211 times 10 to the negative 9 meters. So the meters are going to cancel. You'll be left with 1 per second. So the frequency will be equal to 1.4 times 10 to the 15 1 per second, or hertz. Okay, so that we can plug that number up here. So 1.4 times 10 to the 15 1 per second. And then all we have to do then to get the energy is to plug in Planck's constant. So E is going to be equal to Planck's constant, which is 4.14. times 10 to the negative 15. And this is electron volts times seconds. So your seconds are going to cancel. You'll be left with electron volts. And this would come out to be 5.8 electron volts. Okay, so at this wavelength, the metal would have this much energy. It only takes this much energy for it to escape, for the electrons to escape. So the remainder would be kinetic energy. So we will subtract from this 4.94 electron volts. We can go out to the tens place here because now we're subtracting. So our answer then would be 0.9 electron volts. So the kinetic energy would be, this is the amount of energy that would be left over, in essence, from what is required for those electrons to escape from the metal. So the energy that they would carry with them would be 0.9 electron volts. Okay, so the electrons that escape would have this much kinetic energy with them. Okay, so that is all of the problems for Module 11. And those are the types of problems that will be on your test covering Module 11. Thank you.